Algorithms and Computational Thinking Part 2. Lesson 5.4, Algorithm Complexity. So what we're going to do in this section is we're going to actually look at code and talk about the big O notation from the code. So for example here, again, the two things you want to kind of look out for, loops and recursion. So notice here, int x equal to 12. That's an assignment statement. That only happens one time. So that's constant. If x is greater than 5, that's constant. That they're going to check that. It's either true or false. I'm never going to wrap back around it. So that's a constant line. X equal to x plus y. That's an arithmetic and assignment statement. That's only going to happen one time. Else, that's a one-time thing. X is equal to x minus 2. That's a one-time thing. So every single line in this code, print x is only going to happen one time. So this is a constant algorithm because everything's big O of 1. All right? And remember, we look at the dominant big O, right? So like if we had a big O of n somewhere, then that would become the dominant term. But everything's big O of 1. So the dominant term here is big O of 1. This is a constant algorithm. It doesn't matter what you assign x to. Every step in this process is only going to happen one time. Okay, so again, there's no loops, there's no recursion. Those are your two big things to look out for. Okay, so here I have a little bit more going on, okay? So here we have int x is 0, that's big O of 1. Int n equals 10, that's big O of 1. If statement is big O of 1, oh, but then we have this loop. Okay, so this is kind of what we need to realize is inside of our code. Okay, remember this is worst case scenario. So is it possible that this does not get run? Yeah, it's possible, but worst case scenario, if our inputs are changed, this code could run, right? So when we do a big O notation, it doesn't matter if it's inside of an if statement. It doesn't matter if sometimes it doesn't get run. Could it ever be run? That's kind of what you're looking at here. So everything else is constant. The if statement's constant, the else statement's constant, the assignment statements are constant. It's this loop. This loop is going from 0 to n. This is big O of n. Now inside of it, I don't have another loop. Inside of it, I just have a linear part. So this is big O of n times big O of 1, which is still big O of n. Okay, so if we look kind of at the complexity here, these are nested, so they technically do get multiplied together. But again, if you multiply these together, it's still big O of n. So I'm just going to kind of mention that here. Right, that's big O of n. So we have a big O of n part, which means that is the dominant term. That big O of n compared to constant, that's bigger. That's going to take over in the long run. Right? Remember, the polynomial example we did earlier, we always look at the dominant term only. We don't care about the constant. So if we had big O of n plus big O of 1, the big O of 1 no longer matters because the n is taking over. All right, here's another one. Okay, let's kind of just focus on the loops here. So we have a for loop here. All right, this is big O of 1, the print statement. So that one's really not, big O of 1 gets overshadowed by the big O of n. But I want you to notice here we have another loop. So here we have a big O of n loop. And then nested inside of it, we have another big O of n loop. So the constants don't really do it. Constant 1 times n is still n. So I honestly, I'm going to just ignore the constants because they, in the grand scheme of it, they don't even matter here. But we have a big O of n loop inside another big O of n loop. Well, remember, nested means we have to multiply those. So that's going to become big O of n times big O of n, which is going to give us n squared. So because these big O of n's were nested, they get multiplied together, which gives us a quadratic algorithm. All right, let's check this one out now. Okay. By the way, going back to that one, if this for loop had not been nested, if this for loop was not indented, we would not have to multiply them. It would have just been big O of n. Okay, because you had a big O of n and then you had another big O of n later, there's still big O of n. It is technically 2n, but we don't care about the 2. So make sure you're paying attention to this indentation here. Like, you have to understand, are these nested or not? Okay, so for this one's got a couple things going on here. Obviously, I'm going to kind of ignore the big O of 1 step. So this is big O of 1. We have a loop. And inside the loop, we have a print statement. Well, we're like, oh, well, a print statement is big O of 1. But what are we printing? We are printing this factorial output. So that means we can't just look at this code and be done. We can't just say, oh, this is big O of n, and that's it. We need to figure out what's happening in factorial, because every time this loop runs, this factorial function is going to run. So we need to figure out the big O notation for factorial. Okay, so let's look at the big O notation of this. All right, well, we've started off if n is 1 constant, return 1 constant, else constant. Oh, we have a recursive function. This is, remember, this recursion is almost like a loop, right? We could rewrite this as a for loop. So this factorial function is big O of n because it's looping back on itself about n times. And it might be n minus 1 time or n minus 2 times. Overall, remember, we don't care about the minus 1, the minus 2. It's n times. In worst case scenario, it's going to hit it about n times. So this recursion is a linear loop, essentially. So we have to be very careful of that because we have a big O of n for loop, and then nested inside of it, we have a factorial function that is big O of n. So we need to be very careful. Again, loops and recursion, you gotta be on the lookout for those. So this is actually nested. It's a big O of n with a nested big O of n. This is also going to be a quadratic algorithm. Okay, it's not as clear, it's not as obvious as the other one was, but it is still quadratic. We have a big O of n nested inside of a big O of n. So be careful of those function calls, and if they're recursive. It's possible that the factorial function, if it was not recursive, it might have been big O of 1. It might have been constant, and then it wouldn't have really mattered. But this one was recursive. It was big O of n. You could have a function with a loop in it. If there's a loop in it, then it would be big O of n, or maybe n squared, depending on the loop. So you kind of have to think about, okay, let's treat this function separately. What's the big O notation of the function? And now let's go back to our main code and put that big O notation there where the function is. All right, so here is, I wanted to show y'all an example of the Fibonacci sequence. Y'all, it's terrible. This is the Fibonacci sequence. Okay, so in the main code, we're like, oh, this is constant, but it's not really. Because it's going to call the function Fibonacci, or fib. The recursive step is adding 2 recursive parts. This is going to double. Every time this function gets called, and it's getting called recursively, so it is looping on itself. Every time this function gets called, it doubles. This is terrible, guys. This is the example of the exponential, the big O of 2 to the n. Honestly, this is the only one I've ever really encountered. I know if you ever use recursion twice in one function, you're going to have exponential growth. So this was just kind of showing you what that looks like. It's not good. There's probably a better way of doing this with a loop or something. Okay, so not necessarily recommended. Okay, so we've seen some examples. I've tried to give you tips on what to look for. So try this one out, pause the video, see if you can figure out the big O notation for this, and then come back when you're ready. All right, so for this one, this is actually a cubic algorithm, and this one was a little tricky. I want to only focus on the loops, okay? So notice, oops, there's no function calls, okay? So you did not have to worry about recursion there. We had a for loop, another for loop, and here's a for loop. So every other line in this is constant. So I'm just going to kind of ignore the other lines. I don't, like, they're not really that important in the grand scheme of things. So let's talk about, how did I get cubic out of this? Well, this is big O of n, because this is going from n to 0, so it's going to traverse n times, essentially. This one up here is big O of n because it's going from 0 to n. The fact that it's adding by 2 doesn't really matter. It's still going to grow linearly. Okay, so I plus 2, I minus 2. You can add or subtract anything you want. We ignore those constants, so that doesn't really affect the fact that this is a linear algorithm. All right, if it was just those two loops, then this would just be linear. All right, they're not, these two loops are not nested, so they're independent of each other. Big O of n is the maximum capacity here, so like that's what we would go with. But this one has a nested loop. What is the big O for this? Okay, so this is where the tricky part came in. This one goes from 0 to n squared. Okay, it doesn't just go to n, it goes to n squared. So we can add and subtract numbers to n. They don't matter. But when you start multiplying your n, that matters, because multiplication of bases causes your exponent to grow. So this interior loop is actually quadratic. Well, we can just ignore this bottom one now because this has just overtaken this whole thing. So we have a linear loop multiplied by a quadratic loop. That's where the cubic came from. The cubic came from big O of n times big O of n squared. Okay, so it was really these two things. All the constants didn't really play a part. This big O of n got overshadowed. So, I mean, even though it was there, it's no longer the dominant term. That's basically, that's the nastiest part of the code. That's where the algorithm complexity is going to come from.